Hwang from Taiwan, Academia Sinica in Taipei. So Hsien-Kuei Hwang is one of the main experts, I will say, of analytic combinatorics in the world. For sure, he did his PhD thesis with the close friend of Philippe Lajolet, Jean-Marc Seyert, which was officially his PhD advisor, but working in close link with Philippe Lajolet at INRIA and École Polytechnique. So the PhD thesis was a few years ago, 94, I believe. So where he developed many limit laws for different combinatorial schemes. But beside all his work on limit laws, Hsien-Kuei works also on a lot of other problems which have perhaps more a flavor of number theory. And this is what we have today. In fact, a mixture of both of them. We will have some limit laws and number theory at the same time. So Hsien-Kuei, the floor is yours.
Yeah, thanks, Sil, for the introduction. Good morning or good afternoon or good night, everyone, depending on where you are. So this talk is about the divisibility of binomial coefficients. Most of the materials have to do with the recurrence property, not much number theoretical ingredients. And this talk is based on joint work with Svante Jansen at Uppsala and my colleague Zhongxi Cai. Okay. Oops. So this talk is about the divisibility of binomial coefficients. So more precisely, we are interested in the number of pairs, M and K, such that a given prime is not divisible by the binomial coefficient M choose K. For those pairs less than n, for example, and we denote this function throughout by f, capital Fn. In particular, if p is 2, then we get the number of odd entries in the first n rows of Pascal triangle. Okay, here is a more graphical illustration of the.
Sorry, I think that you have a problem. You see only the first slide.
Only the first slide.
It's the same thing for you, Wissam?
Yes, I confirm.
Oui, c'est resté bloqué sur le premier là.
So then, how to solve this problem?
Can you push the arrow to the right or something like this, please?
I can freely change pages here, but I don't know why this change of page doesn't go through.
Are you using Acrobat or something equivalent?
Acrobat, yes.
We don't have the same format. If you push on the arrow next to 1-35 on the next to the paginations, try to push the arrow, please.
Okay.
Sinon, Hsien-Kuei, tu peux essayer de partager peut-être tout l'écran plutôt que juste. Ah, ok, ça marche.
It's working now. You are on page 3.
Okay, and then
you are on page 2. Good.
Okay.
Now on 1. Okay, perfect.
Now it's working. It seems that full screen doesn't work.
Okay, then it's better to come back to page 2, please.
Okay, so then I can do this. Okay, so on the left we have the classical Pascal triangle, and if we single out those odd numbers, then we get the figure on the right. So which is the primitive form of the usual the famous Sierpinski triangle, where we remove the center, remove the unilateral triangle inside recursively, as you can see from the figure near the bottom. Okay, now you are still on page 3, or
Yes.
Okay, so maybe I should do this. Okay, then, okay, then this way. Then already change page?
Page 4 now.
No?
We are on page 4 right now.
Page 4. Yeah, that's correct. So then we are interested in how many odd numbers, how many odd binomial coefficients. One of the early results by Gleicher in 1899 states that for each column, so the nth row of Pascal triangle, the number of odd numbers in the nth row of Pascal triangle is given by 2 to the nu of n, where nu is the number of ones in the binary expansion of n. As you can see from the figure there, where we circle all the odd numbers, all the odd binomial coefficients by red. And on the right, you can see the total counts, which correspond exactly to the 2 to the nu n, as well as nu n as the first coordinates. So far so good. And when adding all these odd binomial coefficients up, we get this function fn, which is numbered A60046 on Sloan's OEIS, Online Encyclopedia of Integer Sequences, where you can find more information about this sequence. So in particular, this counting sequence satisfies the divide and conquer recurrence, as I more precisely fn is 2 times f the floor part of half n plus 1 time f evaluated at the ceiling part of half n. Written, if we expand this recurrence, we get when n is odd, when n is even, it's 3 times its half. And if f is odd, then it's 2 times its half plus fn plus 1. And from this simple recurrence, we can easily get the estimate that fn is bounded above by n to the log 3 at log base 2. So this is the crude estimate. And we can, of course, get other properties like generating functions and so on. And
Hsien-Kuei, we are still on page 4.
Sorry, I forgot.
Yeah.
So it seems that it's better I don't go full screen. Is that okay?
Yeah, it's okay.
And now page 5, right?
Yes, page 5.
Okay, good. sorry. So on this page, I talk about the recurrence satisfied by the counting sequence of the sum of 2 to the nu of n, okay? Which is the total number of odd binomial coefficients in the first n rows of Pascal triangle. So the crude estimate, beyond the crude estimate, n to the log 3 at base 2. Can we do better? And one old result by Stolarski, 1977, states that if we normalize this, so the counting sequence by n to the row is the log 3 at base 2, then its value fluctuate between one third and 3. And that's a very good estimate. And he also refined this by saying, he also showed that the limit sup of this sequence is larger than 1, larger than or equal to 1, while the limit inf is bounded about by this 0.81 and so on. So as we can see from the figure, indeed, if we normalize capital Fm by n to the rho, we get a nicely placed and nicely behaved periodic function, which is indeed of fractal nature. And this means that if we zoom in any place, for example, if I zoom in the region near 0.4, then I get this very similar shape of the behavior. And similarly, if I continue zooming in the local, I get the figure on the right. Yeah.
Sorry, Christian, just to be sure of the notation, big F of n was the number of odd guys less than n?
The total number of odd binomial coefficients in the first n rows of a scale triangle.
Okay.
Okay. Which is the sum of 2 to the number of ones for the parameter less than n. And there's a, yeah. So then the same year, Harpos refined Stolarsky's result by proving that the limit sup is indeed 1, while the limit inf is given numerically by this 0.8125 and so on. But the problem of exact characterization of this constant or this limit beta remains open. For concerning the periodic oscillations, we can say much more. And actually, there are many papers in the literature, like Fourier expansion, Holder continuity, and irrationality of the point, minimizing this periodic function by Lache, almost sure differentiability or the fractal nature, and so on. And here are some references on this page. And the conjecture by Harpos is that if we define this sequence, n0 equal to 1, and nr plus 1 equals twice n of r plus or minus 1, depending on which one minimize gives a smaller value of p. Is it true that for all r, this gives always the sequence minimizing or achieving the minimum value of the periodic function? And this remains open after so many years. Okay. And for p larger than 2, we can say more. We ask the same question. So what is the minimum of the periodic function arising from counting the total number of pairs for which a given prime is not divisible by the binomial coefficients m choose k for all pairs less than n. So what's the minimum of this periodic function? Same question. For example, here I show a few figures for the periodic function for p equal to 3, 5, 7, and 11, and p is always a prime.
Hsien-Kuei, it is not yet clear that it should be a periodic function, so you will prove it?
Yeah.
Okay.
Just to give you the highlights at the moment, just to give you a quick idea of what's going on and what's similar to the case when p is 2 or the other binomial coefficients. So here what I plotted is I superpose all the periodic functions of each interval of p to the k. For example, for p, when p is 3, this point corresponds to 3, 1, 2, 3, and this is 1, this is 3, 4, 5, 6, 7, 8, 9, and so on. So each window of p to the k is now superposed in the same unit interval. So then their figures are superposed one after the other. And you can see better the fractal nature of this plotting. Okay. So the higher the value of P, the more cusp or the more valleys you can observe. Some classical results. So this type of questions, I mean, the congruential properties of binomial coefficient in general, has been studied long ago by our ancestors. For example, Legendre, he showed that the highest power of P divided n factorial is given by m minus the new P of n, which is the number of sum of digits in the binary expansion of n divided by P minus 1. And for Kumar, 1852, it shows that the highest power of P that can divide n choose k is the number of carries when you add k and m minus k in base P, and so on. And you can find good surveys in Stolarsky's paper and Singh Master Gonville, 1997. The books by Dixon also contains a large number of useful references in the 19th and 20th century. Okay. And Stein in 89 showed that for general P, he derived the limit sup and give bounds for the limit inf. So the limit sup is, as in the binary case, equal to 1. The limit sup for the periodic function arising from Fn normalized by n to the rho. Rho now represents log p plus 1 choose 2 at base P. And the limit inf remains undetermined. Of course, there are some bounds, but they are not exact. In general, extremal values coming from periodic functions, especially of fractal types, are difficult to characterize. Now results for this beta. So now we focus on the minimum value of the periodic function. As always, I denote by rho the log of p plus 2 choose 2 at base P. So Volodin conjectured and later proved by Franco, beta 3, in the case when P is 3, we have this exact value, which is 2 to the log 2 base 3 minus 1, around 0.77. And Wilson also, based on more analytical and numerical evidence, he conjectured that beta 5, beta 7, and beta 11 are given by these expressions. And his key observation, which is also useful in the following discussion, is that the minimum value of P always occurs at some points head of S, such that all but the finite number of its base P digits equals P minus 1 half for P minus 1. Okay, this is the key observation. So for example, even when P is 2, you may, sorry, this is not correct. Is that correct? P minus half. At some point, such the final number of base 2 equals 0.11. Not in the case of a binary, this is not true. Okay. Here are some notations for the theorem. Given pairs C and eta, where C is any integer between 1 and p minus 1, and eta is any integer between 0 and half p minus 1. And we define this head of S, which is 2 C plus 1 divided by 2p minus eta divided by p squared. In terms of the binary expansion, we can write it in this form, which is 0. C is the first digit, and then the next digit is half p minus 1 minus eta, and then all others are p minus 1, half p minus 1, okay, until infinity. And then we define this b C eta to be the binomial of C plus 1 choose 2 times this 1 plus this fraction and times this factor. The theorem says that for p from 3, any prime between any odd prime, and only odd, between 3 and 113, with a proper choice of C and eta as given in the list here, then the minimum value is achieved always at this point. Yeah. S, which is S. Okay. In particular, when P is 5, 7, or 11, this proves Wilson's conjecture, or Wilson's conjecture is true. Okay. Our approach to this theorem is based on the divide and conquer recurrence. So capital Fn, this sequence satisfies this recurrence, which is the sum of p minus j times f in the integer part of n plus j divided by p for j ranges from 0 to p minus 1. Then once we have this recurrence, we solve the recurrence by the theorem, by the theory we developed earlier, which shows that we have indeed this behavior. So capital Fn equals, this is actually an identity. There is no error involved. It equals n to the row times the periodic function, where this periodic function can also be explicitly characterized by this, by A. A is the binomial, is p plus 1 choose 2, to the 1 minus fractional part of t times this function phi. And this phi is defined in this form. Given a number in its binary expansion, it can be defined by half times this series of finite products, okay, in terms of the digit here. And then the last stage, once we have this solution, then the last stage is basically a numerical recipe, which consists of two main parts, which we call magnifying mapping together with a piecewise monotonic modularization. More details below. Let's begin with the divide and conquer recurrence. The simplest one is of this form. So f of n is equals alpha times its floor part, half n floor part, plus beta times f, the half n seeding part, plus another function which we often call tau function. And the solution in most computer algorithm literature is given roughly by this type of simple approximation, a simple heuristic. Roughly, if we just ignore the floor and the ceiling, then we get this quick solution, which is in most cases quite correct. And this calculation is also quite effective. in that it gives you a very quick estimate of what's going on there concerning the growth behavior of this sequence. And it's often used, the so-called Messer theorem is often used in computer algorithms. So if the total function is small, more precisely, it's small O of x to the rho, or big O of x rho minus n. Then in this case, the gross order of this f is always of this form, big O of x to the rho. And if G is of this order, of the same order, x to the rho, then we have an extra log factor. And if G grows larger than x to the rho, then f is of the same order as G. So roughly we say that this is a more dictator regime. And in the first case, when G is small, this is mostly like a normal regime, like a democratic regime, roughly, in terms of political terms. No politics involved here, sorry. But this type of estimates is too rough. If we are interested in finer, more precise estimate, then this is not so useful. And also, there's no mention concerning the optimal conditions and so on. And we give a solution to all these questions by this elementary interpolation approach. The idea is quite simple. So if there exists an interpolation function, phi of x, such that it bridges smoothly f and fx plus 1, so fn or mn plus 1, okay? Then the recurrence involving floor and ceiling function can actually be extrapolated to a continuous function such that it satisfies the very simple recurrence, which is easier to solve, much easier to solve, as in the last page, where we mentioned that there's pretending that we don't have this floor or ceiling function. But now with the idea of interpolation, then we can actually confirm that this is correct, provided that this interpolation function exists, and which is guaranteed by this lemma. So if alpha and beta are positive, then there exists a unique continuous, strictly increasing function, phi of t, such that this sequence f of fn, when extended to a real function, satisfies this simple recurrence. Fx equals to alpha plus beta times f half of x plus g of x. The sum of the interpolation function are plotted here. Alpha, beta, 2, 1, 1, 2, 3, 1, and 1, 3. You can see it basically some vector nature. And this function phi actually can be written in explicit forms using the binary expansion. Yeah, as you can see the sum here. In particular, if alpha is equal to beta, then this interpolation function is simply the linear function. Okay, so this is the basic construction. And then our main result concerning the divide and conquer recurrence says that if this Q is defined by this series, and rho is given by this log alpha plus beta base 2. So if we define this series Q of x in this way, then if this Q function converges uniformly for x belonging to the interval 1, 2, then this is an optimal condition for f of x to be equal to x to the rho times the periodic function minus q. So this is not only asymptotic when Q is of smaller order, but also an identity for this function f of x. And in particular, this function p is continuous, and we also have this series form for the periodic function. Okay. Some remarks here. So uniform convergence is needed to guarantee the continuity of the periodic function. And the master theorem we just saw is well justified and optimized because here we have an if and only if condition. And as I mentioned, this is not only asymptotic, but also an identity for any integer n larger than or equal to 1. And indeed, this holds for if you replace n by x so that it holds for all positive real. And in a special case, when f is of small, is of O, big O of n to the row, if we are just interested, if we don't care about the exact calculation, we are just interested in big O estimate for the gross order of Fn, then we need weaker conditions, like this partial sum is big O of 1, which is the partial sum of this Q. If this is bounded, then we have this big O estimate for Fn. Okay, and we also characterize other smoothness properties like Lipschitz continuity or Herder continuity, and we also derive the absolute convergence Fourier series under some conditions. Okay, so this is the theory that we built a few years ago. And this result applied to hundreds of examples in many different contexts, including computer algorithms, cellular automata, arithmetic functions, and most of them from OEI sequences, a few hundreds of them, combinatorial structures.
Sorry, Hsien-Kuei?
Yeah.
Sorry. For all those examples, is it the case that it's still an exact identity or just a first order approximation, and then you have some error term?
Yeah, it depends on the tau function. If the tau function is so, as you can see, as long as your tau function g, yeah, can be so. The condition is that as long as you as the sequence can be nicely interpolated so that it is continuous, and if this Q converges uniformly, then we have this exact result.
Okay, so this is the if and only if condition here. Okay.
Yeah, yeah.
May I intervene, please, in the same direction? In the same direction, could you go back, please, to 17, page 17?
17, okay. Yep.
The first equation in the box is quite familiar iterative equation. Probably you are aware of the direction of works of Cook's map, for instance, to solve this kind of equations. F of x, something with f and plus an additional function. Knowing j, you can recover quite easily f.
So you mean that?
Do you get the formula which is just below also, or something else?
Yes, the first formula in the box.
Yes, but from the first formula, then you, by iteration and so on, you get the second formula. The solution that you have in mind, is it leading to a similar shape or something else?
Okay. With much more shape. This kind.
Actually, sorry. Actually, the proof is simple. So you split into odd and even cases, and you write down the corresponding. You expand the corresponding recurrence in the odd case and even case, and you check. You check if with the availability of this interpolation function, then the same result, the same recurrence holds, and that's the proof.
No. I mean you can recover entirely F with J because in this the second equation in the box,
Sure.
F is expressed with F. What of course the second expression relies on a recurrence, but what I was trying to say, there are the works of Marek Kuczma on this kind of iterative
functional equation.
maybe you are probably aware of this. Huh? Sorry for interrupting you.
Okay, no problem. Yeah. So in this equation, if as long as x divided by 2 to the m is like bounded, then we can express completely in terms. So express f of x completely in terms of g.
Okay.
Okay. A simple application is to the generating polynomials of the number of ones. Okay, in the binary case. So this generating polynomial satisfies this recurrence. Sorry for this notation. I didn't write it. So it satisfied this. This recurrence with alpha and beta equal to 1. Yeah, beta equal to 1. Alpha is not 1, and g is 0. This is notation with f1 equal to 1. So in this case, this has been studied in many different papers in the literature, and this result is well known, as I also mentioned. So we have n to some order times a periodic function. And many years ago, together with Peter Gabner, we proved that the Fourier expansion of this periodic function p is absolutely convergent for alpha in this interval. And this range actually can be refined to all positive alpha by a different theorem in the theory of Fourier series. Okay, I skip this part. And so after the binary case, because we are dealing with the binary case, so we need to extend the framework from binary to binary. Here's the general framework. So assume we have this recurrence. So the idea here is that in the case of binary, we have half n floor and ceiling. And in the case of binary, the idea is to split these p parts as evenly as possible. So that gives this n plus j divided by p, and you take the integer part. Yeah. So this may be referred to as the balanced binary divide and conquer recurrence for general p, because we try to balance each part so that they are as evenly as possible. Okay, so assume we have this type of recurrence together with some initial conditions with this lambda given. Then we define this constant. If we sum over, so A is the sum of all these leading coefficients, and rho is the log A at base P. So the theorem says that if all these leading coefficients are positive, if none of them is 0 or negative, then we have the same type of behavior. Yeah, f of n equals n to the rho times the periodic function. And here, the periodic function, as before, can be it's continuous and periodic. It can be computed in this form. Everything quite explicit in terms of the decreasing power of A and I think this and these two parts. One is partial sum, and this is the final product. Okay. So if we apply the theorem, then we get immediately that the count is now back to this capital Fn, which is the number of p, not device number of binomial coefficients less than n in the first n row, roughly. Not p is not divisible by no, not divisible by p. Sorry, and it satisfies this n to the row times periodic function. The question is, what is the minimum value of this periodic function? Okay. So for convenience, I define this function g of s, which is a to the minus log s at base p times this phi of s. In terms of this, then the minimum value of p actually is to minimize g in a slightly different range. And the constant, the coefficients that we defined above, s hat and b of c eta. Now the situation is clear. So the coefficients, the constant b of c eta actually equals g evaluated at s hat, and s hat is given by this form. This is the same as the expression that I give for b c eta before. Okay. The method that we use to compute to prove that the limit inf of the or the minimum of the periodic function is given by this b of c eta or beta is proceeded by the following steps. So first we fix capital M and small lowercase m with m in this range. So between 1 and p to the m, and define this mu to be the midpoint of this interval. So m divided by p to the m, m plus 1 divided by p to the m. Then we define a linear mapping from unit interval to this I m plus k. M plus k is defined by this mu plus a smaller quantity, half to the left and to the right. And this theta k of t is defined by m divided by p to the m plus every digit is half p minus 1 and plus something else. And this something else is taken, t belongs to is any number between 0 and 1. So with this definition of the linear mapping, the midpoint that we choose here equals theta k of half. And if m, the binary expansion of m is given by this form, then we have, then mu can be written in this way. So this gives a correspondence between these numbers and the relations. And one nice feature of this definition is that once we have this mapping constructed, then the difference between phi of theta k of t minus phi of mu is given exactly. We have this closed form expression for their difference, and roughly this expression says that we magnify the difference of this function near the local to a global estimate. Yeah, so involving phi of t minus phi of half, and this phi, maybe I think I recall this function. Yeah, maybe it's somewhere here. This function, where is it? Yeah, phi is defined this way. It's a yeah. So this function actually is not easy to such difference is in general difficult to estimate, but the local, because we want to prove that for example, mu is the real minimum. Then we zoom in a smaller neighborhood of this minimum, and using this relation, we can transfer the difference on the left-hand side to a global estimate involving only phi of t and phi and a half. So this is often easier because of the fractal nature. This gives a nice access to the local difference. This is one of the key steps. Okay, the next step, the difference, because our aim is to prove to establish the minimum of the function of G. So we consider the difference in terms of phi. G is defined this way. So it's a to the minus log s 8 base p times phi of s. And once the difference of phi is known, and this function this is a well-behaved function. The leading part, a to the minus log s over p, actually is differentiable. We can use Taylor expansion and so on. So it's very well-behaved part, while this phi of s is less manageable. So first we have this difference involving phi in the local parameter, and then when considering the difference of g of theta k of t and g of mu, then we have this expression, and which can be q is defined here, where we have a constant tau. Tau is given by this expression, the product of 1 plus a 1 until 1 plus a of m divided by a to the m. So roughly this q involves the difference between phi of t and phi and half and t and half. So this is quite good because we avoid to fight in the local. Everything now transferred globally to the easier estimate. So the theorem says that if this q is larger than E is defined this way. Yeah, it involves the product of phi of t and phi and a half and t and minus half for some k. For all t in this range, then the minimum of G is actually reached at this point, mu. And this minimum is unique in this range. So this is a tool that we use. So first we bring local to global, and then we prove this inequality. If this inequality holds for t in these two intervals, then we prove that this point mu is the minimum in this range, mu minus 1 over 2 p to the m plus k and so on. And outside we need a different approach. And to check whether this inequality holds, we split into two cases. So the first half and the second half in the unit interval. And as you can see on the right-hand side, the factors involved are easier to estimate. And then to here we observe we can split them in a way. We can split the difference Q and E in a form that they are the difference of two monotonic functions. In the first half of the unit interval, they are the difference of two decreasing functions, and in the second half of the unit interval, it can be expressed in terms of the difference of two increasing functions. So then the idea is simple. If we have two increasing functions, for example, and then if this we take the we take the smallest for the first function and we take the largest for the second. then if the difference remains positive, remains larger than a constant, for example 0, then the difference is always larger than this constant for all x in this range. So this is very simple monotonic modularization technique. And then to check numerically that this holds actually for the global range, then we split into smaller intervals, and in each interval we check this condition. And this is the way that we use to check. For example, when p is 3, I think I'm running out of time. So when p is 3, then we follow the same idea to check if this q minus E1 is positive in this interval. And then if this is true, then we can be certain that this S hat, which is 3 over 2p, is the unique minimum of G in this interval. Okay, and then to check that, we split into equally spaced small intervals, and trying to find larger numbers of splits for each interval. For example, in the first half, we take n1 equal to 9, and then for the second half we take n2 equal to 7, and in this case we can give their difference is given by the numerical table here. Okay, and once this numerical calculation is done, which can be easily repeated. Okay, then we justify that this is actually the unique minimum of this function in this local range. And outside this range, we use the same idea by splitting into equally spaced subintervals and check the inequality if G of S is larger than G of mu, okay, or S hat. And this is the idea. And of course, the details are quite messy. Okay, I'm skipping. So, for example, this is the plot for G of S for p equal to 3 and p equal to 5 and 7 and so on. Yeah, and this is if we zoom in for S in the interval 1 over p and 2 over p, then we observe this behavior. Okay. This shows how the Q and E behave in the unit interval. Okay. I think I'm running out of time. I have to skip. So the same method of proof applies to all odd primes larger than or equal to 3 with different choices of C and eta. We did this for p up to several thousands, and it's always observed that with the proper choice of C and eta, the minima is always reached at the point that we choose, namely this kind of S hat that whose expression is given above. Well, you may think that these pairs of C and eta is monotonically increasing. And here is some strange observation. So when the prime is between 1973 to 1987, the choice of C and eta corresponds to 4 and 50. And in the next is 490. So this eta, the value of eta decreases, not monotonically increases. And so we checked this several times because the first time when we saw this, we thought there might be an error, and actually it turned out to be correct. So that it's not always monotonically increasing. So this complicates somewhat the general proof. If one really wants to find a more general proof for all primes. Okay, and this is for p equal to 13, 17, and 19, and so on. I think this is not that useful. For large p asymptotics, we can find a very good estimate for the Xi and eta. Okay, based on, but if assuming that we have the minimum is always at this expression, then we take derivative with respect to Xi and eta and solve this equation. Then we get quite good estimate for the values of Xi and eta. And for large P, we can also get some asymptotic approximation. And as I mentioned already, so although P equals, in the binary case, it seems to be the simplest and easiest, it turns out to be the most difficult because the characterization of the minimum value of the periodic function remains open so far. And for P for P larger than 2, for each fixed one, we can prove by the same numerical recipes given here. But the proof that this is true for all odd P remains open. Okay, and the approach also applies to many other recurrences. And for example, multinomial coefficient, gray codes, or their quinary extension generation and so on. A more general approach to finding the minimum value remains quite wanted. Okay, thank you very much.
Okay, thank you a lot, Hsien-Kuei. Clap, 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 clap. So any question in the room?
And why this transition of phase in slide 31?
Page 51.
31,
No.
31.
31. Okay.
Okay, why this transition of phase from have you some idea or some explication?
I think this is purely numeric. I don't think there's any type of phase transition stuff here. It's maybe because of small number effect. We don't know yet, because going beyond all these numbers requires quite intensive numerical calculations, which is heavy.
Okay. Please, if you can go back to slide 23.
23. Yep.
Okay. The last equation, the right-hand side is free of k, but the left-hand side is we have a root to the power k, and we have k.
Yeah.
It is free of k, the right-hand side of the last equation.
Okay, let's see what's going on here. So the left-hand side involving k. So your question is that the left-hand side involving k, while the right-hand side doesn't.
Doesn't
okay.
k.
Yeah. Okay, so actually k is the k involves in the definition of, I think this is okay, 1 plus. There's no typo here. Just trying to see why. Okay.
This also applies on the box above. Nu should depend on k, but on the
Sorry, Rafik, what was the question?
So the question, so his question is that the left-hand side of the last display involves k, while the right-hand side doesn't.
But isn't it kind of hidden in your AM?
Yeah. No, a is a constant. A involves only p, no k. So k is finite. So we choose probably a constant k such that this holds true. I think this is if we go back to the calculation, let me check
Okay.
the proof. Let me check the proof. Where is that? Oh, it's here. Okay. Yeah. Right here.
Maybe because mu equals to theta k of 1/2, and the
Yep.
mu it is equal to m plus half divided by p to the power m.
Yeah, and then actually in the proof, I think the dependence on k is cancelled. Maybe I can show you here. So I think I can share each time only a window. I don't know. I don't know if that helps if I move it here. So
We still see the slides. We still
it's
see
the
the
same
slides.
the other slides. So then I have to okay, let me share. Loom is here. No, this is not. Where is it? It's here. So then I stop sharing this one. I show you the proof. Okay, and then how can I do that? Share. And then what is that? Bino divisibility, and it should be this one. Okay. Okay, so
Okay.
this is a proof for lemma 3.2. So do you see this?
Yes.
Yes, we see it.
Yeah. So as you can see in the proof, that
Okay.
on the right hand side, so we have k here, and we have k here, but they are cancelled because of this definition of a. So then there's a p to the k here, but p to the k when we move to the left hand side, then we are totally fine.
Okay.
No problem.
Okay.
Yeah.
Thank you.
No problem.
And so now can you go back to the slides?
So, okay, then I repeat the same process. Okay, just
Okay, but good catch, Rafik. It was not a trivial answer.
okay. Then I share this. Okay, now back.
Yes.
So
Thank you.
Yes, okay, so we have PK times the okay, yeah. So yeah, so it's a funny phenomenon, in fact. Yeah. So I don't have a question, but rather a comment. Can you go back to one of the curves that you had showing the periodic functions? Perhaps at the very beginning, you had some of them and with their
This one?
fractal. Yes, for example, those ones. Yes. Yes. So just a comment because in your field, we often call this periodic function, but on the drawing, they are not periodic. And it is because if you go back to your definition uh, of the stuff with the fractionary part of number, then in fact it's periodic if we don't plot it with respect to the fractionary part of log n.
Mhm.
Because in several places you say, oh, it's a periodic function of period one, but on the drawing it's not easy to see.
Yeah.
So I don't know if you had one slide, perhaps just earlier, when you show this the relationship with the fractionary part of log n. I think that when you had the definition of P, possibly it was written.
Yeah. Some place, yes. I think somewhere. Some here,
Okay,
for example.
yes, exactly. So here we see it. Yeah, exactly. So because here you did the change of variable with the fractionary part, then it leads to these drawings which are a kind of rescaling of periodic function. So it was
Yeah.
just to explain the word periodic, which may be confusing for some people. It's indeed periodic, but the plot that we had was after the renormalization in one sense. Okay, so is there any other questions?
Okay, since you mentioned this periodic function, I think one remark that is worth of mentioning is that you may be wondering why P2 is more difficult to characterize its minimum. If you look at the figure, okay, if you look at the figure roughly, just to give you a quick idea, so you see that there are two very close, two minimum that are very close here. And if you continue zooming in, you see them here. And then because of the fractal nature, so that to exactly identify them becomes less trivial. Well, if you look at, for example, 3, you don't see this. Okay, 5 don't see this, but 7 you see, oh, they are also close, but this is basically due to numerical errors because I just truncate. These are huge numbers, so if you pinpoint to more precise location, probably this nearness property will be clearer. Yeah, that's another remark. Yes, sorry for using more time.
Okay, fine. Okay. So is there any further remarks?
Just
Yes.
Yeah, Wissem, I believe, wanted to say something. I heard some voice. No, I know perhaps it was Feti.
Yes. This is Fatih Belgasim. Yes. Can
Yeah,
I say
so-
something to the
Please.
professor? Yes, I want to look at the slide before our approach, what it says less or equal to 113.
13. Yeah.
Yes, Salam. There is one condition there that says less or equal to 113.
Less than or equal to 113. Yeah, this is just
113. 113.
Yeah, 113.
Yes. Okay.
Yeah.
The first remark that I will leave, it's an open remark. It's maybe the number this number is very important. It's less than 114. 114 is the number of surahs in the Quran. But anyway, and you can disregard that. But for the time being, I think that the patterns that you have, and I've studied a little bit of this, have to do with if you look at the groups made by P. In other words, they generated the simple groups, the ZPs. And division is related to in most cases with the P's is related to the way that the generator in the ZP generates the group. And so like the sequence that you have 0.A1, A2, A3, and then you have P plus 1 over 2, P plus 1 over 2, etc. I think that the sequence has to do with the sequence of the members or the numbers in the group itself that are generated by the generators in the ZP group. In other words, there is a connection between this theory, the division theory, and between the way that the ZP group behaves as a simple group as being generated by the generator in the ZP. There is a correspondence. There is some correspondence between the way that the elements of the group are generated and the pattern of the because it's a division problem in the end.
Okay, thanks for the remark.
Thank you.
Just a small.
Thanks.
Just a small.
Interesting.
Just small question in slide 15. Okay. The function f is an integer function or not? F,
Which
capital F, the first function.
Yeah.
Fn.
That's
Fn is an integer function or not?
Is an what?
Integer function is in the set
Yes,
n or not?
it is.
It
Yes,
is.
it
Okay.
is.
But Fn is equal to n to the power rho multiplied by some function which is it is not an integer function.
Both of them, you have n to the row and p, both of them are not integers. So the product of two non-integer can be an integer.
Must be an integer. Okay.
No,
Okay.
can be. And here it is the case.
Okay, must be. In this case, must be.
Yeah,
Exactly,
sure.
exactly. Yeah,
Sure.
yeah. And that's why this identity is a little bit nice and surprising. It's not clear in
it is
advance that you
surprising.
could have something that nice. Yes, exactly.
Yes.
Yeah.
And
it's very common for this type of problems.
Okay. The next slide, 16, just a simple remark. In the equation 1, n is x. G
N
of
is-
x and not g of n. And log of x in the master theorem.
Oh, yeah. As a typo, yes.
Okay.
Okay, good catch.
Okay.
Yeah, okay.
Thank you again.
Okay, thank you.
Okay, any further last comments, feedback, question? So if no, thank you again, Hsien-Kuei.
Thanks, everyone.
Clap, 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 clap.
Thank you very much.
Okay.